Today's topic is root locus. So what is root locus? Root locus is basically the locus of roots. So now we should ask ourselves the question, which roots are we talking about exactly? And it corresponds to the closed loop roots because they define the stability of the system. And it's a graphical method, so we draw the plots. So basically to summarize, root locus is a graphical method to understand how the closed loop poles move as the system parameter k varies. Welcome back everyone. I am Teja Golla, a fifth year research scholar working under Dr. Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. Let me share my screen. Can you see my screen?
Yes, sir.
Today's topic is root locus, and as I have mentioned, it's a graphical method, and I will also be showing the MATLAB simulation so that we can verify whatever plots that we are drawing, whether they're correct or wrong. And I'll also show how to write the MATLAB code and how to verify it using MATLAB. In the beginning, I'll discuss about the rules of the root locus and what it actually means. And for every rule, we'll also solve one problem to understand how to apply that rule. Parallelly, we'll verify using MATLAB simulation to understand and verify how to use MATLAB. And then eventually we'll get to know all the 9 rules of the root locus, and then we'll solve a couple of problems. And then we'll draw the root locus of particular problem, and then again we'll verify using MATLAB. So just to state, root locus is a graphical method. So in the given system, we have a system parameter k, and that is varying. System parameter k. Varies. So let me consider one system. So here say I have k, and here g of s is the plant, and h of s is the feedback. And then if I complete the circuit, say R of s. Now, if we check the closed loop transfer function from the input to output, what will be the input to output transfer function? It will be k into g of s by 1 plus k g of s h of s. As explained in the previous classes, this is the characteristic polynomial. And then we are now understanding the roots of this characteristic polynomial, which will define the stability of the system. And how are we doing that? By varying the k. So k is a parameter that we can vary. Here it is considered to be a gain, but it can be part of the system anywhere. But for simplicity, we are considering it to be separate from the system transfer function. So we'll be varying k and then see the roots, how they are moving. So 1 plus k into g of s h of s equals to 0. If we solve that, we'll get the roots. But without actually solving that polynomial, how are we going to draw the root locus? So that is all about today's discussion. We'll have certain rules that we'll follow, and then using those rules, we can draw without actually solving this equation. So this equation is 1 plus k into g of s h of s is equals to 0. So this is the equation, and these are the closed loop poles. and they define the stability of the system. So now using root locus, we'll see as the k varies, how long will be the system stable, whether varying k will unstabilize or destabilize the system, or whether the system is entirely stable as long as k is varied from 0 to infinite. So k is a positive constant because it's a gain, it can't be negative. Uh, so we'll vary k from 0 to infinite and see how the poles are moving. So if you consider this equation, 1 plus k into g of s, h of s is equals to 0. So this is the solution for this characteristic polynomial, right? So if you calculate it by keeping g of s, h of s in the other side, we'll get k is nothing but minus 1 by g of s, h of s, right? So this is the value of this k. So as long as this k becomes minus 1 by g of s, h of s, that is the roots of this equation. And let us assume g of s and h of s to be a polynomial. Or let us assume this entire thing to be some polynomial transfer function p of s. So from this equation, we can get that p of s is minus 1, which means the magnitude of p of s is 1 and the angle of p of s is 180 degrees or odd multiple of 180 degrees. So we can write it as 2k plus 1 into 180 degrees plus or minus again. So it can be plus 180 degrees, minus 180 degrees. So the solution exists as long as this p of s is minus 1. So this is the solution of this equation. Okay. So now k is equals to minus 1 by g of s, h of s, right? So if you consider from this point, and if we generalize, let us say g of s into h of s is a transfer function with m number of zeros as well as n number of poles. I can consider it to be s minus 0, 1 into s minus 0, 2 into up to some s minus say m number of zeros. And then if we come down, we have poles p1, p2 up to some n number of poles. So now I have to find k, which is minus 1 by g of s into s of s. So if you substitute there, we'll get k magnitude. If I calculate magnitude of k, then it will be minus 1 will be removed. So I'll get magnitude of 1 by g of s, h of s. Say at s equals to s naught I am calculating, then I can calculate it as mod of s naught minus t1 into mod of s naught minus p2 up to some mod of s naught minus pn by mod of s naught minus z1 mod of s naught minus z2 up to some mod of s naught minus zn. So we'll substitute that s value, and then at that value we can calculate the gain. So this is how we can calculate the gain, and these are the conditions that needs to be satisfied for any s value to be solution of this characteristic polynomial. So now as k varies, how the roots will move, that is all we are going to study today. So this is just a brief intro about what is root locus and why we are studying it. Now we are going to learn how to draw the root locus, and we'll also learn the different rules. Until this point, any doubts?
No, sir.
Okay. So now we'll start understanding the root locus rules. So there are 9 rules. We will follow all these rules and then we'll draw the root locus. So whenever a transfer function is given, say this is the transfer function, k into some zeros as well as poles. So now how are we going to draw the root locus? So we have to follow each and every rule from 1 to 9, and we have to remember those. And following those rules, we can draw the root locus for any given transfer function. So first we'll understand few rules, apply it, again understand few rules, apply it, and then we'll go. And once all the rules are done, then we'll solve few problems to understand all the rules at a time. So first rule number 1. So the root locus will be symmetric with respect to the real axis. So whatever is above the real axis will be on the below side. So if you draw on one side, you can just do the water image and you can get the other side. So that is the rule number one. The root locus is symmetric about the real axis. It's about the real axis, and each root locus has branches. So each how many branches does given transfer function has? It will be equal to the number of poles, and the number of branches in the given root locus is equal to the number of poles. So how many poles it has? It will have same number of branches. So if you consider this example, how many poles it has?
Two,
Poles, sir. 3 poles.
Three
three,
poles, right?
three.
One is at
Three.
origin, minus 2, minus 4. So
Mm.
for this given transfer function, we'll have three branches. So this is rule 1. Okay. So once we apply it, then we'll understand more, because now we are just like reading out rules. It will not make any sense until we apply it. So I'll just write down the rules and then I'll explain and correlate with the problem. Then it will make more sense. So the second root says that all the root locus start from k equals to 0, and this k equals to 0 happens when we are at the poles. So as the gain tends to infinite, we'll be reaching towards the 0. So first let me write and then I'll explain why it is like that. So all the branches of the root locus start at poles, and then these poles means it is k equals to 0. So we are drawing the root locus from k equals to 0 point to k equal to infinite. So they start at poles and end at zeros. And at zeros. So this means k is tending to infinite. And what happens if, say, number of zeros are lesser than the poles, right? In this case, there are two zeros, right? And three poles. So we are supposed to start from the poles and end at zeros. So we'll start at three poles. How are we going to end at two zeros, right? We are starting from three poles. In that case, it will actually be going to infinite, because when we have two zeros, one is at minus 1, minus 3, we can consider there is another zero at infinite. So one of these pole will go to infinite. So whenever the number of zeros are more than number of poles, then some of these branches will move towards infinite. So that is also part of rule 2. So some of these branches will go to infinite. So the number of branches terminating at infinite is equals to number of poles minus number of zeros. Sorry, number of zeros. Yeah, number of poles minus number of zeros. Again, if the rules are a little bit vague now, I'll try to explain once we solve the problem, then you'll understand better. Now coming to the third rule. So any point on the real axis, any point on the real axis lies on the root locus if the sum of number of poles and number of zeros to the right hand side of that point is odd number. Okay. So before I explain point three, I would like to add some more context to point number two. So here you can see that K is this, right? Let me see. Yeah. Okay. So this is the solution that we got from that characteristic polynomial. So if you consider S naught to be any pole, right? Say S naught is P1. We are starting at P1, which means K equals to 0. So that's why any point that is lying on the root locus is first of all characteristic polynomial solution, and that also satisfies this equation. So at K equals to 0 means all the poles are solution. So that's why the root locus start from the poles, which means K equals to 0, and as the gain increases we'll reach towards the zeros, because if you substitute the zero this becomes infinite. So that means K is equals to infinite. So we'll start at poles where K is equals to 0, and we'll end at zeros, which means K is corresponding to infinite because they are in the denominator. And this is what we got from the characteristic polynomial, and this is the solution, which means only closed loop poles will be satisfying this equation. So that's why the root locus starts from the poles and end at zeros. So if you have any questions, you can ask us, like ask me, else I'll solve one problem trying to explain these three rules.
Locus. No, sir.
Okay. So starting with problem number one, I will copy paste the rules so that you can correlate it better. So these are two rules, right? Okay. And this is the third rule. Okay. So for this problem, how many branches are there? For this transfer function, how many branches will be there in the root locus? Number of branches is equal to number of poles, right? Yes, Saurabh says 3. Yes. So the number of branches of this root locus are 3. And the number of branches that will be terminating at infinite will be np minus nz. So what is np minus nz? So I'll write down each of these points. So we have number of branches equals to 3. And how many of these branches will be terminating at infinite, which is equals to number of poles minus number of zeros. So how can we get this information? Number of poles minus number of zeros. So what is np minus nz?
1, sir.
In 1, right?
1.
So the number of branches, sorry, I made a mistake. Number of branches is not infinite. Number of branches is 3. Branches is equals to 3, and one branch will move to infinite. One branch will go to infinite. Okay. And then third rule says any point on the real axis lies on the root locus if the number of sum of number of poles and zeros to the right hand side of that point is odd number. So let us draw the uh, axis. So we have, I think we can keep the axis little towards the right side because everything is on the HP. So as I have mentioned in the last class, poles will be represented by X mark and zeros will be represented by O mark. So we have poles at 0, -2 and -4. So we have 0, one is 0, and so this is, I'm not according to scale, so I'm considering this as -2, then say this is -4. So these are the poles. Now zeros are -1 and -3. So I have zeros at -1 and -3. So we know that the root locus starts from pole and at 0. So how do we know whether this pole will go towards this 0 or this pole will go to this 0? So for that we'll try to apply the root 3. So any point on the real axis will lie on the root locus if the sum of the poles and number of zeros, sum of number of poles and zeros on the right side of that point is odd number. So if you see, if I consider this point, to the right side of that point, only one pole is there, which means this point is a solution of the root locus, because to the right hand side of this point, there are odd number of poles and zeros combined. So this region will be part of root locus, agree? Because onto the right side, there is only one pole and it is an odd number. So this is part of root locus. Agree, everyone? Is this point clear?
Yes, sir.
So this pole is basically going to this 0. So it is going to the -1. So this point is corresponding to k equals to 0. And then this point is corresponding to k tending to infinite. So as k tending to infinite, the closed loop poles will move from O to -1. And whether the root locus will be there in between -2 to -1. So if I consider any point, if I consider any point here, say if I consider any point here, how many number of poles and zeros are there on the right side of this point?
Sir, 3 poles, sir.
No. If I consider this point, how many poles and zeros there are there on the right hand side of this point? Like to the right hand side of this point, how many poles and zeros are there? Are you getting my question?
There are no poles, sir, in right hand side.
One
Sorry,
pole
-1,
and zero, right?
-1 and -1 and 0.
Yeah, so two are there, which are even number. So if it is even number, then root locus doesn't exist in this region. Root locus only exists if on the right hand side, there is odd number of poles and zeros combined. So in this region, it doesn't exist. So it exists again in this region, right? Because if I consider any point in this region, on the right hand side, I have two poles and one zero, combined is 3, which is an odd number. So again, this pole will go to this 0. Okay, and again root locus will exist in this region, because on the right hand side we have how many? 3 poles and 2 zeros, which means I have 5 total combined. So this root locus, like this entire axis also will be part of the root locus. Now, if you ask me, this pole is going towards this 0, this pole is going towards this 0. Where is this pole going? If you come back to point number 2, the number of branches terminating at infinite, because as I have mentioned, 0 can be considered at infinite. So this pole will go to infinite as k is tending to infinite. So this point is again k equals to 0 point. This point is k tending to infinite. Similarly, this point is k equals to 0 point, and here we will get k tending to infinite. So this is how the poles will move towards the 0. So is this part clear?
Sir. Yes, sir.
Yeah. Any doubts, anyone?
The root locus is valid for negative feedback system, sir, or positive feedback system, sir?
So it is valid for both negative feedback as well as positive feedback, but the rules will change. And whatever is the syllabus of this course, it is only for negative feedback. That's a very good doubt that you have asked. So whatever we are learning, it is only for negative feedback. So the rules are slightly different for positive feedback system, but in this course, only negative feedback are there. Yeah, thanks for pointing this out. So it is applicable for both negative feedback as well as positive feedback, but we are only learning negative feedback, and rules will slightly change.
Okay, sir.
Because
Thank you,
here
sir.
instead of -1 we'll get +1, because there will be one minus here. So instead of 2k plus 1 into 180 degrees, we'll get 2k into 180 degrees, product of 360 degrees, something like that. And rules will change here and there slightly. Here it is odd number, there it will be even number. So slight change will be there, but it is equally applicable. So this problem is clear, right? Everyone, if you have any doubts, you ask me, else it will, the like, difficulty will increase. So if you have any doubts, I'll clear, else now we'll move to MATLAB.
No, sir.
This
Okay,
okay.
sir. Good.
Okay. So now every time it is also equally important to check whether what we are doing is right or wrong, because we are humans, we make mistakes. So we can use any toolbox, and then to the toolbox we can feed this transfer function and then check the root locus. So there are commands to the uh, draw the root locus. So here I have root locus.m. Again, I will be sharing this into the drive. You can access these MATLAB files from the drive. So these three commands are simple. Clear means it will clear this command window, and here there is something in the workspace. So if I do clear, it will clear the workspace. So now nothing is there in the workspace. And close all means if any plots are open, it will close. And then CLC means it will clear the command window. So now I have to define the numerator as well as the denominator of the G transfer function, right? So if you go back here, I have G two first order, right? One is s plus 1, one is s plus 3. So now I can use this conv, which is a function. So in that function, I can give two inputs. So two polynomials I can give. So polynomial input, the coefficients has to be in the square bracket. So I will give s plus 1 is this, comma, another one is s plus 3. So 1 and 3 and semicolon. And then denominator has 3, right? But I can combine these two and write it as s square plus 2s. This is s plus 4. Because this function conv can take only two inputs, two polynomials. So I have to combine any of these two. So I'll write s square plus 2s plus 0. So s square plus 2s plus 0. Then the other one is s plus 4. So 1 and 4. So now G is transfer function with numerator and denominator. G displays something that will display in the command window just to cross check whether my inputs are correct or wrong. Now now I'll be considering figure 1 to plot, and I will do R locus of G. So root locus of this G, and then grid on and hold on is to add the grid, and then hold on because we are trying to do something. And these are just different type of uh, comments to set the Times New Roman font and font size as 24 and width. So these are just to play with the settings of the graph. So let me quickly run. So if I run, I have to first check whether the transfer function is correct or wrong, because I can enter a wrong number here. So numerator is s plus 1 into s plus 3, denominator is s into s plus 2 into s plus 4. So now let us check the plot. So this is the plot. So from 0 it is moving to -1, from 2 it is moving to -3, from 4 it is going to infinite. So is this matching with our plot? 0 to -1, -2 to -3, -4 to infinite. So this is matching. So this is how we plot. So this is just a few comments that we will understand as we do more problems. And it is simple. The plot, like the command is still here, but the bottom ones are to set the Times New Roman font, all those things. This font and everything. And we can zoom in here and see how the poles are moving. So if you click at any point, then it will give the details of that point. So here the gain is 0.609. So if I want to delete it, I'll delete. So if I start from here, right, the gain is basically zero, close to zero. And if I click here, the gain is going towards infinite. So it is gain is 52.2. So as we increase the gain, how it is changing. So if we go towards the pole, then the gain will be very high. So if I delete this and go towards the pole, gain will be high. So 128. So the gain zero starts from this pole, and then this is a zero. So as the gain increases, it will move from pole to zero. So is this concept clear, everyone? Any doubts until this point?
Yes, sir. No, sir.
Okay. So if the concept is clear, because we have taken a simple problem, but as the complexity increases, the root locus will have different type of combinations. So then we need to have knowledge of other rules. Then we'll apply those rules, and then we'll solve the problem quickly. So it will be easy. So the NP minus NZ, number of poles minus number of zeros branches that are terminating to infinite, that are these basically point 3, point 2, some of them are terminating at infinite, right? So these branches that are terminating at infinite will move along asymptotes. Will move along the asymptotes. Will move along the asymptotes with angle. So basically these that are terminating at the infinite, they'll move along these asymptotes and then they'll have an angle. So let us consider the angle as well. So the angle is given by phi angle of asymptotes is nothing but 2k plus or minus 2k plus 1 into 180 degrees by number of poles minus number of zeros. So this is the angle of the asymptotes. So we have to check whether NP minus NZ is there or not. So if they are there, some of these branches will be terminating towards the infinite and they'll move along these asymptotes. And the angle of the asymptotes is given by this. So now we also have to ask at what point this asymptote start. So that is called centroid point. That is our point 5. The point of intersection of these asymptotes, the point of intersection of these asymptotes is called centroid. And the centroid is defined as sigma A. So sigma A is given by summation of poles. So it is summation of all the poles minus summation of all the zeros by number of poles minus number of zeros. So very simple. In a given problem, first we have to check the three rules. First rule is what? Number of branches is equals to number of poles. Sorry, yeah. Number of branches equals to number of poles. Second rule says that the root locus start from the pole and it will end at the zero. And NP minus NZ branches will terminate towards the infinite. And third rule says that any point on the real axis lies on the root locus if summation of number of poles and zeros on the right hand side is odd number. Number 4 is whatever branches that are terminating at infinite, they'll move along the asymptotes with this angle plus or minus 2k plus 1. We can consider plus or minus, not both, okay? Because we'll move from either 0 to 360 or minus 180 to 180. We'll consider one circle. It is easy to consider 0 to 360, else it will be confusion. And then the point of intersection of these asymptotes is called centroid. And centroid is given by this expression, number of poles minus number of zeros, summation of poles minus summation of zeros by number of poles minus number of zeros. So is these two rules also clear? Now we'll apply
Yes,
this
sir.
on another problem. So in this problem, can you tell me how many poles are there? So we'll move from first point to fifth point, whatever we have learned all, so that it will make our life and concept clear. How many poles are there? NP?
Three poles, sir. S
Three
equal to
poles.
0
And
and
number
Z.
of zeros?
There are no zeros, sir.
No zeros. So number of branches in the root locus are how many?
Three, sir.
Three. Very
Number of
good.
pole
So
equal to number of branches.
yes, very good. So these are the number of branches in the root locus. I think I'll try to avoid this green color because I don't think it is properly visible. Sorry about that. Okay. So now what does second point says? Second point says that it starts from k equals to 0 and it will end at infinite. And how many such branches will end at infinite? NP minus NZ, right? So NP minus NZ branches will end at infinite. So how many of these branches will end at infinite? All the three branches will go to infinite, right? Because there are no zeros. No zeros means all the zeros are at infinite. Is that clear?
Yes, sir.
Okay, NP minus NZ is 3. And then point 3 says that those points are lying on the root locus so that on the right hand side, the summation of poles and zeros are odd number. So we'll see the third point. Okay, so let me quickly draw. I will draw with a light color so that dark color, this is the I'm drawing with a very light color so that I can use black color to draw the root locus rather than green color, which is not visible. So first thing what we have to do is always find the roots and then the open loop roots and then plot them on this plane S plane. So what are the poles and zeros values?
0, sir, plus 3 minus 3.
Yes, very good. Plus 3 minus 3 j, right? J.
Yes, sir.
So let us draw that. We have 1 at 0. We have 1 at 0. 1 at say plus 3. 1 is at say minus 3. So this is 0. This is plus j3. This is minus j3. So does root locus exist on this region, in this entire region? How can we say, whether can we say that using point 3? So what does point 3 say? On the right hand side, we have to count the number of poles and zeros. So on the right hand side of this, whether the poles and zeros
Left hand side, sir.
on the right hand side. So what does any point on the real axis lies on the root locus, and if the number of poles and zeros to the right hand side of that point is odd number. So now we have to ask whether if I'm considering this region on the right hand side of this entire region, how many poles and zeros are there? If it is odd number, then that is a part of root locus. So is this part of root locus?
Yes, sir.
Yes, because the number of poles and zeros on the right side is odd. Again, there is less than a minute, so kindly join back if this meeting ends. So this entire thing is part of root locus, okay? Which means this pole is basically going in this direction, infinite. All the poles are going towards infinite, but we don't know the direction. So in order to know the direction, we will have to use this 4 and 5, which is asymptote's angle and centroid, the intersection point. Okay. So point 3 is done. If this meeting ends, kindly join back. Okay. So now the angle of the asymptotes can be obtained as sigma A is equals to plus or minus 2k plus 1 into 180 degrees by number of poles minus number of zeros, which is 3. So we'll get plus or minus 2k plus 1 into 60 degrees. So I can say that my sigma A, if I go from 0 to 360, I'll have 60 degrees, 60 degrees, then into 3, 180 degrees, then into 5, 300 degrees. So these are the angles of the asymptotes. So this is how we calculate the asymptotes, which is plus or minus 2k plus 1 into 180 degrees. Divided by number of poles minus number of zeros, which is 3. And then I am going from 0 to 360 degrees. So I have substituted k equals to 0. Then 2.
K is equal to 1.
1. Yes. So 60 into 1, 60 into 3, 60 into 5. So this is, sorry, not sigma A, this is phi A. So now we have to also calculate what is sigma A. So this is the angle of the asymptotes. But what is the intersecting point? So that is given by sigma A, which is nothing but summation of poles minus summation of zeros by number of poles minus number of zeros. So can you tell me what is this value sigma A for this question? Number of poles minus summation of poles minus summation of zeros by number of poles minus number of zeros.
Sir, sigma number of poles.
Summation of poles minus summation of zeros.
Sorry, sir,
So
number of poles.
yeah, by
1,
number
sir.
of say,
1.
why it is 1?
1, sir. Sir,
Summation of poles is how much?
summation of poles is 1, sir. 0 plus 3 and minus 3.
So summation is 0, right?
Yes, sir.
And number of summation of zeros?
Summation of poles is, sir,
0.
plus 1. Yes, sir. Summation of pole is 1.
How it is 1?
0 and summation of sorry, sir.
How summation of poles is 1? It is 0, right? 0 plus j3 minus j3.
But sir, 0, sir. 0 is the another pole. There are 3
Ah,
poles, sir.
Yes, yes. So summation of the poles means 0 plus
Oh, yeah,
J3
yeah.
minus J3, right?
These are imaginary pole. Yes, sir.
Yeah. So it is 0, right?
Yes, sir.
So 0 minus 0 by 0. 0 minus 0 by 3. So the sigma is 0. So the asymptotes are starting at 0 and these are the angles. So first we have to draw the asymptotes angles. So this is 60 degrees and this is 300 degrees. So this is 60 degrees and this is 300 degrees and 180 degrees is basically this line.
Yes, sir.
So now we know that the poles are moving along this axis. So this pole will move along this axis. This pole will move along this axis because we already know that this is part of the root locus and this pole will move along this axis. So now this will go towards this and then this will go towards this. Is that clear? Using asymptotes and then centroid point. First we have to calculate both of these and then draw the asymptotes. Then we'll understand how the poles are moving. Is this concept clear for this problem? Hello.
Sorry, sir. Can you repeat, sir?
Yes, yes, yes. So I'll just
Sir,
repeat the entire problem.
sir, this line is referred to the asymptote or root locus
Yes, so the
plus
blue
J.
lines are asymptotes, black lines are the root locus.
Okay.
So these are asymptotes. So the poles are moving towards the infinite, right? Infinite, towards the zeros. But how do we know
Okay, sir.
how they are moving? So for that we have to draw the asymptotes. So how do we know the angle of the asymptotes and center point? So that will come from this phi a and sigma a. So once these two are calculated, then we'll draw these lines. And then now the poles will move along those lines. So this pole will move along this line, this pole will move along this line.
Yes, sir.
And then this pole is going to infinite along this line because
Infinite.
this we got
Yeah.
from the part 3. Sorry, rule
Okay.
3. So this is clear, right? Asymptotes and
Yes, sir.
then this. Yeah. So now the question is at what angle this will depart? That will come in the upcoming rules. So at that time we'll solve this problem. So keep this in mind. So at what angle it will depart? So this is called angle of departure. Angle of
Departure.
departure. So similarly, angle of arrival is also there. At what angle it arrives at the zero. So these are they are discussed in the upcoming rules. Once that rule comes, then we'll try to solve such problem and understand. So now let us do the same exercise. We have to plot the root locus using MATLAB. So numerator is 1, right? Only 1 is there. There is nothing. So I'll put 1. And denominator has 2, or I can convert it into single polynomial, which is s cube plus 9s. So I will write denominator also s cube plus 0s square 9s plus 0. Is that clear how we write the numerator and denominator? Numerator is 1, denominator is s cube plus 9s. So s cube plus 0s square plus 9s plus 0.
Yes, sir.
So now let me run and then check. So my denominator is fine, right? 1 by s into s square plus 9. So this is my transfer function, which means these two are correct. Whatever I have given entry is correct. Now let us check the root locus. So if you see the root locus, so it is starting from here, this 2, here it is starting from -2, and then here it is starting from 0. So these are going infinite in this two directions, and this is going in this direction, which is also matching with what we have drawn here. Is that clear?
Yes, sir.
Okay. So other everyone, it is clear, right? Chidananda, you're also following, right? Okay. So now let us move to rule 6. So rule 6 is called break in and break away point. So let us write this. So the break in and break the break in or the breakaway point. So what is break in or what is breakaway? the break in or breakaway point can be calculated by solving dk by ds is equals to 0. So what is break-in or what is breakaway? So again, we'll solve one problem to understand this. So dk by ds is equals to 0. So what is break-in or breakaway point? So whenever two poles are moving towards each other, they will hit at some point and then they will start diverging. So at what point they will hit, that is called break-in or breakaway point. So till now, whatever examples we have considered, they have not come across such situations. So now let us consider one problem. And then in this problem, we'll face such issue and then we'll see how to solve this. So again, we'll start from rule number 1 to 6. So what? How many poles are there? Can you quickly tell
3
number
poles,
of
sir.
poles? 0. Yeah.
3
And what
poles,
is
sir.
your name? Sorry.
Sir, Amresh, sir.
Amresh. Okay. And then, so how many of these branches are there?
3 branches, sir. Number
3
of poles is equal
branches.
to number of branches.
Yes, very good. Number of branches. How many of these branches will terminate at infinite?
Branches terminate to infinite.
NP minus NZ, right?
Yes, sir. 3, sir.
3.
Yes, sir.
Okay. So now we'll see on the real axis how many, what is the region that will lie on the part of the root locus. So this is the root locus RL on the real axis, right? We'll see what is the region that lies on the root locus. Now coming back to asymptotes. So we can calculate the
Yes, sir.
asymptotes. So let's start with phi A. Phi A is what? Plus or minus
the
2k plus 1.
61,
Yes, yes.
so 0 degree for 60, 180.
0 is not possible, right? K starts from 0, right?
Yes, sir.
16,
Yes, sir.
180,
K is equal to 300.
300. Same as the last
Yes, sir.
problem. Very good.
Yes, sir.
So
Same as
let
the
us
last
calculate the,
question.
yeah. Let us calculate the centroid also,
Yes, sir.
which is sigma
Number
p
of poles minus number of zeros.
summation
So
of
3
poles minus
minus
zeros. No, not number of poles, summation of poles.
summation of poles. Yes, sir. 2 plus 2 plus.
Again, pole is not 2, pole is minus 2.
What? Yes, sir. Minus 2. Minus 4, sir.
Minus 4, very good. So it is minus 4. So with this information, let us try to draw the root locus. Then we'll come back to the sixth point, which is break-in or breakaway, because we'll try to understand that. Okay. So minus 2, minus 4, minus 6. So let me quickly draw the root locus. So we have minus 2, minus 4, minus 6. So I have something like this. So this is the axis. Now I am considering minus 2, minus 4, and minus 6. So this is a minus 2, this is minus 4, this is minus 6. And asymptote start from minus 4, and then the
Minus 4.
angles are 60, 180, 300 degrees. So let
Yes, sir.
us draw those also. This is one asymptote. This is another asymptote. And this is another asymptote. So these are the asymptotes. So now first we'll find out on the real axis, where does the root locus lie? Between minus 2 and minus 4, whether it lies or not?
Minus 2 and minus 4.
In this region. Maybe I'll point out this region. So this region that you see minus 2, minus 4, whether root locus lie or not.
No, sir.
Why no? Or why yes for both? Like what is the logic behind it? Based on the third rule, real root locus lies on the real
Okay.
axis if summation number of poles plus number of zeros is equals to odd number, right?
Yes, sir.
So to the right hand side of this, whether the poles and zeros are odd or even, summation of poles and zeros in this region.
Odd, sir.
Odd, right? So root locus lies in that region, right?
Ji, sir.
Now in between -4 and -6.
Yes, sir.
Between -4 and -6 also it lies. So here we have root locus between -2 and -4. Okay. So between -4 and -6 also do we have here in this region? How, like every time I ask this question, you have to see on the right hand side number of poles and number of zeros, whether it is odd or even.
-6, -4, sir.
Yeah, between -6 and -4.
Sorry, sir.
Okay, I'll explain. I think this point is not clear. I'll re-explain. So on the real axis, root locus exists. Okay. So in which region does it exist? So in order to find that, we have to check. Say you consider certain region between pole and zero, all given poles and zeros, and then you have to see if the root locus exists in this region on the right hand side, whether the number of poles and zeros summation are odd or zero. Say if I start from this point, say I'll start from zero, okay? I'll start from this point
0.
and then I'll move to this direction, okay? So first I'll see on the right hand side how many poles and zeros are there. Zero, which is even number. So in this region, there is no root locus because on the right hand
-2
side,
to 0. Yes, sir.
yeah, there are no zeros. Now I'll start between this region, -2 and -4. I will see in this direction how many zeros and poles are there. I will see only one is there, which means odd number. So in this region, there is root locus. So the trick is same. If the root locus exists here, it will not exist here and it will exist here. It will not exist here, it will exist here. Like similar logic, but again, we have to check. Let us check. In this region, whether the root locus exists or not. Count the number of poles and zeros on the right hand side. I have 2 poles, which is even number. So there is no root locus here.
Okay, sir.
Again, -6 to infinite, I will check. How do I know? On the right hand side, I have to check how many poles and zeros are there. So how many are there?
3 poles.
3 poles. So root locus exist or not?
Exist, sir.
Exist, right? So this pole, it is simple. It will move towards infinite in this direction because it is also along asymptote, right? So this pole will move in this direction along the asymptote towards the infinite. Now these two pole, so this pole also will come in this direction. This pole also will come in this direction, right? There will be a collision at some point in between. Once the collision happens, then one will move along this asymptote in this direction, other will move along this asymptote in this direction. Clear?
Yes, sir.
So now we have to find this point. So this point, the collision where it happens, this is called breakaway point. Breakaway point. So how do we find this point? So we will be using this dk by ds equals to 0. So this equation we have to do. So we have to, we know that 1 plus g of s equals to 0 is the solution, right? So 1 plus k by, so we have to find k in terms of 0. So we know that 1 plus g of s is equals
GS
to
into HS
0.
equal to 0.
1 plus k by s plus 2, s plus 4, s plus 6 is equals to 0. So from this I'll get k equals to minus of s plus 2 into s plus 4 into s plus 6. Agree?
Yes, sir.
So now dk by ds is equals to 0. We have to find the roots of this. This will give us the breakaway or break in. It can be anything. So breakaway or
Point.
break in. Yeah. So we'll see what is break in the upcoming problems. Here, breakaway means they'll hit and then they'll move away. If they hit and then they move inwards, that is called break in, or like they are moving inwards and then they hit. So this is like they're moving inwards and they're breaking away, right? Moving away. Had it been other way, say they're coming from outside and then they hit and then move. So that is break-in point. So now we will differentiate this and then we'll find out what is the breakaway point. And we know that it is in between -2 and -4. So let us first calculate k, expand it. So minus is, let it be there outside. So first I will multiply s plus 2 and s plus 6. So I'll have s square plus 8s plus 12. Then if I multiply s plus 4, then I will get k is equals to minus of s cube plus 8s square plus 12s. Now I'll multiply by 4. 4s square plus 32s plus 12 fours 48. So now I can get k is nothing but minus of s cube plus 12s square plus 44s plus 48. Agree?
Yes, sir.
So now I'll do dk by ds is equals to 0. So minus is removed. So I'll have 3s square plus
Plus
24s
24s.
plus 44 is equals to 0, right? I have to solve this to get my breakaway points to calculate S, right?
Yes, sir.
So just to simple, like to reduce the calculation time, I have written another code in the MATLAB to calculate the roots. So this is called polynomial roots. So you have to enter the polynomial coefficients and then it will display the roots. So my coefficients are 3, 24 and 44. 3, 24 and 44. So if you click run, so basically this is the polynomial. This is the roots that it will calculate and then this will the display. So this is another code. So the roots are -5.15 -2.84. Minus
Yes, sir.
5.15 -5.15 -2.84. So calculating the roots can be done in the leisure time.
Yes, sir.
But just to
Yes, sir.
save time, I have written the code. I'll also be uploading the code so you can also use it if you need. If you see, there are two breakaway points, -5.15, -2.84. So whether this can be -5.15 or -2.84. This point,
Minus minus 2.84.
-2.84, right? Because -5 is
Yes, sir.
somewhere here.
Yes, sir. Minus
So
2.84.
yeah, very good. So this point is basically -2.84 because it does not mean all the S is breakaway point. So breakaway point is a solution of this, but all the solutions are not breakaway points. So there can be valid points, there can be invalid points, but depending upon the root locus, we found that this is my breakaway point, and at -2.84, these two will hit and then it will move away, which means this pole will move slowly, this pole will move fastly because both will hit at the same gain. So this pole is moving faster, this pole is moving slower. Once they hit, they'll move at the same pace. So the black color is the root locus. Final root locus is uh, this will come in this direction, this will come in this direction, they will hit and then they will move towards the asymptotes. And then this is simple, this will be moving towards the infinite in this direction. So now let us do on the MATLAB and see whether whatever we are doing is correct or wrong. So k by s plus 2, s plus 4, s plus 6. So the numerator is the again root locus. So numerator is 1. And then in the denominator, I will be using CONV. Okay. And CONV can take only two inputs, two polynomials. But I have how many? But I have three, right? So I'll use nested CONV function. I will show how. So first, what I will do is s plus 2, s plus 4, right? So s plus 2, comma, s plus 4. So once this is done, now I'll write another CONV and the input is s plus 2, s plus 4 and the other input is s plus 6. So is this clear how I have done this? Basically, I
Yes,
have
sir.
considered nested CONV. The inside one is s plus 2, s plus 4 and the outside is s plus 6. But we may make a mistake, so that's why I'm displaying it to see whether the input is correct or wrong. So it says there is some error. We have to see what is the error. So there is one bracket that is missing there. Yeah. Again, there is an error. There is comma here, not full stop. So yeah, these are mistakes that we make and then we'll have to rectify it. So now if you see display is fine 1 by s plus 2, s plus 4, s plus 6. Let us go to the MATLAB. Yeah, if you zoom in, so this plus symbol is for zoom in. If you zoom in, 1 is -2, -4, -6. -6 is going to infinite. But 2 and 3, they are coming and hitting at one point. Let us find whether the point that we got is correct or wrong. So this is -2.845, which is what is matching. We have considered till two decimals, so -2.84. So this point is also matching. It is hitting and then it is moving towards the infinite. So it is hitting and then it is moving at 60 degrees, +60, -60, or 300 degrees. So if you draw an asymptote, it is starting from -4, right? If you see the as if it is moving towards -4. Similarly, you can see if you extend this, they'll meet at this point. So this will help us to draw the root locus accurately uh, using asymptotes. So this is another such example where there is a breakaway point. So is this point also clear? Till now we have learned how
Yes, sir.
many? 6 rules. So now there is 3 more rules, 7, 8, and 9. So rule number 7 is one such rule. 8 and 9 are a little bit different. So I can move to rule number 7, right? Amaresh, right?
Yes, sir.
Okay, okay. So rule number 7 is about angle of departure or angle of arrival. So we will see this. So this is basically, if I say this is angle of departure or angle of arrival. Angle of departure or angle of arrival. So wherever we are departing or wherever we are arriving from that for that pole, we have to calculate the angles from the other poles and zeros. So now uh, we will have the angle phi net angle of all poles plus net angle of all zeros. So now whether this will be plus or minus, so that is also very critical because some of the poles are there in the numerator, some of the poles are there in the denominator, right? So if you see here, poles are there on the denominator and zeros are there on the numerator, right? So
Yes, sir.
zeros will have positive, poles will have negative. So that is also very important thing. Just a minute. Where are we? Here. No, here. So poles will have minus and zeros will have plus. So minus theta p plus zeros angle and then plus this angle of departure, I am calling it phi, will be plus or minus 2k plus 1 into 180 degrees. So basically, we are getting it from here only. So basically, if you see, we are getting from this criteria. Angle should be plus or minus 2k plus 1, 180 degrees. And how is that angle defined? Angle is defined by angle of zeros minus angle of poles plus that angle of departure, that will be plus or minus 2k plus 1 into 180 degrees. So now this is the equation using which we'll calculate the angle of departure slash angle of arrival. We will understand it better once we solve the problem similar to the previous cases. So let us consider one problem quickly, then it will be relatively easy. So, yes. So using this equation, we'll calculate basically theta p and this is theta z. So all angles, basically all zeros and all poles. I have considered one example using which we can understand this easily. Okay. So I have considered this example. G of s is k into s plus 2 by s plus 3 s square plus 2s plus 2. So we'll start from the first rule. Number of poles, how many poles are there? Amaresh, how many poles are there?
Sorry, sir. My mic is mute. There are 3 poles, sir.
Yeah, yeah, very good. So there are 3 poles. How many zeros?
Sir, one zero, sir.
1 0. Very good. So how many of these branches will tend to infinite?
3, sir.
NP minus NZ, right? Number of branches are 3. How many of them
Sorry,
will go
sorry.
to infinity? Yeah.
Answer
Number
2,
of
sir.
branches, yeah. Number of branches are 3. Branches
10 to infinity.
tend to infinity is NP minus NZ, which is 2. And then rule number 3 is we have to see the root locus on the real axis. Root locus on the real axis. And then he said that on the right hand side, summation of number of poles plus number of zeros should be odd number.
Yes, sir.
On the right hand side. So yeah. So we'll do this same set of sequence for all the problems. So it will also revise all the rules. So you will be, by hearting the rules once we do it like in a loop. So now we'll come back to 4, which is 5a asymptotes, right? 5a is what? Plus or minus 2k plus 1 into 180 degrees by NP minus NZ is what?
2.
2. So what will
2,
be the
sir.
angles?
K is equal to the number of poles is 3. 60, 180, 300, sir. Because there are 3 poles.
No, NP minus NZ, right? It is not only
Uh,
poles.
NP minus ZZ are 2, sir.
Yeah. So what will be the angle now? 2k plus 1 into 180 degrees by 2, right? So this is
Yes, sir.
basically plus or minus 2k plus 1 into 90 degrees, right?
Yes, sir.
So what will be the angles for k equals to 0?
K is equal to 0, 90 degrees, sir. And
Uh,
another is the
k
K is
equal
equal
to
to 1.
2.
1.
Sorry, 1. Yeah.
1. K is equal to 1. So 90
90 into 3.
270 degree.
270 degrees. So basically plus or minus 90 or 90 to 70
Yes, sir. Yes,
degrees.
sir.
So now we'll come back to the fifth one, which is sigma A is nothing but summation of poles minus summation of zeros by number of poles minus number of zeros. So for this, we'll have to
Yes, sir.
calculate the poles and zeros, right? So first, let us
3,
calculate what are
3
the
by
poles.
2. That is 1.5, sir.
How did you calculate?
Number of
Summation of poles is
1.5, sir.
summation of poles
Summation
is
of
how much?
poles. Summation of poles is 3, sir. And
But this is also there, right?
yeah, this one is also cancel out, sir.
No, it will not
There are
cancel out,
2.
right? It
One
has a
maximum.
real part, right? Previously, it was imaginary. So s square
Oh,
plus 9, it has real part also, right?
yes, sir.
So summation of the poles in this will be minus 2, right? If you know, like summation of the poles is minus b by a, product is c by a.
So this one, 2, and 2, sir.
Okay. So like say if things are
Minus
not
1
clear.
plus I. Minus 1 plus I.
Yeah.
Minus
Good,
1
good.
plus I.
Minus
And
1 plus
minus
I.
1 minus I.
Yeah, minus 1 minus I. Thank you for
Yes, sir.
calculating. And then minus 3, pole is minus 2.
Yeah,
Okay.
yes, sir.
Yeah. So now what will be sigma n?
Sigma answer minus 1 minus 2 minus 5 upon 2. Minus 5 upon 2. That is minus 2.5, sir.
Okay. Summation of poles is how much? So let me calculate here only so that it will be easy. Summation of zeros is minus 2, right?
Yes, sir.
And summation
And
of
summation of
poles?
poles is minus 5.
Okay. So now what is this? Summation of
Minus
poles minus
2.5.
summation of 0 by number of poles minus number of zeros.
Yes, sir. So 2.5.
1.5, right? Minus 5 minus of minus 2 by 2, right? Summation of poles minus summation of zeros.
Oh, sorry, sir. Yes, sir.
Minus 1.5, right?
Yes, sir.
Okay. So till now we have calculated what we can calculate. Now we have to see whether we will have the sixth rule, which is break in, break away, and then we'll calculate the angle of departure or angle of arrival. So let us see. First, let us draw and see whether we'll come across such case or not. Okay, so let me quickly draw the axis first. So everything is on the LH left hand side. So I'll draw a bigger one and I'll draw almost towards the right side. Okay. So this is the axis we have. And then let us draw the poles. One is at -3. So this is a -3. This is a -3. And then 0 is at -2. 0 is at -2. So this is O. 0 is at -2. And then poles are at -1 plus j, -1 minus j. So this is -1. We have -1 plus j. And then we have -1 minus j. So this is basically -1, this point. Okay. Now asymptotes are at -1.5, right?
Yes, sir.
So this is
Centroid, sir.
-1.5.
This is not asymptote. Centroid,
Sorry,
sir.
centroid. Yeah. Thanks for correcting. This is centroid. And then from this
Yes, sir.
centroid, I have 90 degrees and
And 270 degrees.
270. So one is on the top going in this direction, and one is at the bottom going in this direction. So basically one is going in this way, one is going in this way, right? Asymptotes, one plus 90 and one 270.
Yes, sir.
Okay. So now let us see the third point first. First, we have to always do whether on the real axis we'll have the root locus or not. So first I'm starting with this region -1 to 0. So whether root locus will be there in this region, you check on the right side number of poles and zeros and let me know. Did you get the question?
Sorry, sir. Can you repeat?
From 0 to -1, whether the root locus will be there on the real axis or not. We'll check using this rule number 3, right? By checking on the right side the number of poles
Yes,
and
sir.
zeros summation. Yeah, Chidananda is saying
Yes,
no.
sir. -2, -1, there are odd numbers, sir. So that will be exit, sir.
So 0 to -1, it is there or no?
There, sir.
0 to -1. How?
0 to -1.
Yeah, I'm highlighting, right? You can see the orange color in this region, 0 to -1. This is 0, right? This is -1. From -1 to 0, whether there will be any root locus on the real axis or no. Using the rule 3.
No, sir.
No, right? And -1
Yes, sir.
to -2 on this region. -1 to -2.
-1 to yes, sir. Exit, sir.
It is there.
Yes, sir.
Why again it is there?
Because, sir, the sum of the root is odd number, sir.
On the right hand side. So in this region,
Yes,
how
sir.
many roots and poles are there? On the right hand side of -2, how many poles and zeros are there? Again, these are not, see, -1 and -0 are just whatever I have used to, note down now. So this is -1, this is 0, and this is -1. Okay. So see, the question is simple. I am asking to the right side of -2, how many poles and zeros are there?
There are one pole, sir.
One pole or two poles?
One.
Two poles, right?
There are two.
This,
Yes, sir.
these
Two poles.
two. So it is even
Yes, sir.
number, right?
Yes, sir.
So in this region, now whether the root locus exists or not?
Even number. No, sir.
No, right? Is it clear or am I just pushing you? Like
No,
you're
no, sir.
understanding,
Is it
right?
clear, sir?
Okay. So from -2 to -3 in this
That will be
region,
exit, sir.
that will exist, right?
Yes, sir.
So in this region, there is root locus. So which means this pole will simply go to this 0. Now from -3 to infinite, whether the root locus exists? You check on the right hand side how many poles and zeros are.
Hello.
Yeah, yeah. -3 to infinite.
-3 to infinite.
Yeah, yeah. So in this
No root locus,
location,
sir.
no root locus because there are four on the right side. Yeah, Chidananda, you're also right. So there are four on the right side. So there is no root locus. So now this pole is going to this zero. And we said that two of these branches will go to infinite, right? So this branch is not going to infinite. This branch will go to infinite. This branch will go to infinite. So there is no break in breakaway. One announcement, there is less than a minute. If this meeting ends, kindly join back. So these two will go to along with this asymptote, right? So now the question is, what is break-in, breakaway? There is no question of break-in, breakaway, but there is a question of angle of departure. At what angle these are departing? Yes, right? What will be the angle at which they depart? So that is the question. I think let this meeting end. Once it ends, we'll rejoin and then we'll discuss that. Okay. So now in this problem, there is no question of break-in or breakaway point, but there is a question of angle of departure or angle of arrival. So let us calculate at what angle from this it will depart. So the question is at what angle this will depart. So in order to find that, we have used this equation, right? So we'll be using the same equation and then we'll be obtaining it. So let us take this equation there. So Chidananda says, sir, sorry, my microphone is not working. That's why I'm messaging. Yeah, yeah, no issue, Chidananda. It's all right. So you just, send messages so that I'll be aware whether you are understanding or not. Okay. Yeah, yeah, no issue, no issue. So now we have to find the point for this pole because the angle at which this is going, this will be just the water image because we know that it is symmetric around this axis. So I think Amresh is also joining. So we will be using this equation to find the angles. So we are now finding the uh, breakaway point for this guy. So we have to find the angles made by other poles and zeros with respect to this guy. So let me use which color? Let me use dark green color. So now what is the angle made by this pole? So angle made by this pole is clear, 90 degrees. So what is the angle made by this zero? Say this is theta 1. And then angle made by this guy. Say this is theta 2. So now I have to add the angles of poles with a minus sign and add the angles of zeros with a plus sign plus this angle of departure is equal to plus or minus 2k plus 1 into 180 degrees. So this is what my equation says. So I am finding this for this guy. So his own angle will be 0. So these are the 90 degrees, theta 1 and theta 2. So I have to find theta 1, then I have to find theta 2. So I can find theta 1 because this height is 1 and then base is 1. So what will be theta 1? Theta 1 will be tan inverse 1, right? Tan inverse 1 by 1, which means it is 45 degrees. Now theta 2 will be tan inverse 1 by 2, right? Because this length is how much? 2, right? So theta 2 will be tan inverse 1 by 2. Is that clear? How theta 2 is calculated? Amrish?
Yes, sir, clear.
Okay. So now we have to calculate tan inverse 1 by 2. Again, because I have MATLAB, I know the comment. It is A tan D of 1 by 2.
2.
So it is
So that
26.56.
is,
You can check if you have calculator. So A tan inverse 1 is 545. A tan inverse 1 by 2 is 26.56. So I will write this angle 26.56 degrees. Okay. Now I will add
yes, sir.
all the poles angles and all the zeros angles. So poles will have minus sign. So one is 90 degrees because this pole is corresponding to this pole with 90 degrees. And then this pole is corresponding with 26.56. So plus 26.56 degrees. and zeros has plus sign. So it is theta 1, which is 45 degrees. And then plus whatever this angle of departure is equal to minus of 2k plus 1 into 180 degrees. So can you calculate plus or minus? So I can consider either plus or minus. So now I have to find this minus 90 plus 26.56 plus 45 degrees plus 5. So what is this angle on the LHS side? So repeat from start. Okay. Chidananda, I'll repeat from start. And yeah, one thing I think I have made a mistake is this will be minus 5. Okay. Because this is angle of departure, right? For angle of departure, we are calculating corresponding to the pole, right? So pole will have negative sign. So I think I have made a mistake here. Let me just clarify this. So this will be minus. Okay. Yeah, yeah. So, Chidananda, I hope it is clear till point 5. So we have no question of point 6 because in this question there is no break in or breakaway point. So now we are directly going to point number 7 or rule number 7, which is breakaway angle or angle of departure or angle of arrival. So basically angle of departure, what does it say? We have to use this equation. So we have to see for which pole we are actually calculating angle of departure. So angle of departure is coming for this point as well as coming for this point. So we are calculating angle of departure for this pole. So now we have to calculate angles of all the poles with that pole, angles of all the zeros with that zero, minus angle of departure equal to plus or minus 2k plus 1 into 180 degrees. So because why minus? Because this is also pole, so that's why we'll have minus sign. If it is 0, then we'll have plus sign. So again, this is angle of departure means it is moving from pole, so pole has minus sign, so that's why minus sign. Angle of arrival will have plus sign. Okay. Now I am joining all the poles and zeros and I am finding the angle. If I connect this pole to this pole, I know it is 90 degrees. If I with a horizontal axis or x-axis, if I am connecting this pole to this pole, angle will be theta 2. This 0 to this pole, angle will be theta 1. So now I have to add all the poles with a minus sign, all the zeros angles with plus sign, and again this is minus. So this is minus 5. So this is also minus 5. So this is minus 5. This is also minus 5. So now I am calculating angle of departure, which is the 5. So I have to calculate it. We have to see whether k will put 0 or 1 depending upon how much we are getting here. So is this clear or again should I explain? Amresh and Chidananda.
Yes, sir.
Clear. Okay.
Uh,
So now theta 1 and theta 2 calculation. Okay. So theta 1 is say they have right angle triangle, right? So they have a right angle triangle. So this is some theta and this is A, this is B. We know that tan theta equal to A by B. So from here I can get theta is equal to tan inverse A by B. So like this I have calculated. So for theta 1, A is 1 and B is base, which is 1. For theta 2, height is 1 and base is minus 3 minus minus 1, 2. So base is 2. So one is tan inverse 1 by 1, other is tan inverse 1 by 2. And theta 1 is for 0, so that's why it will have plus sign. And theta 2 is for pole, so that way it will have minus sign. So now we have to calculate this and then find what is angle of departure phi. So minus 90 minus 26.56, right? So if I do minus 90 minus 26.56 plus 45. So this angle is coming minus 71.56. So minus 71.56 minus 5 is equal to, say I'll consider minus 180 degrees. So now my phi is how much? 180 minus 71.56, right? So if I
yes, sir.
consider that, I will use this. So I'll do answer plus 180. So it is 108.44 degrees is the angle of departure. So this is now 108.4 degrees. So this is how we will get. So 108.4 degrees. So if you calculate 108.4 degrees, it is slightly more than 90 degrees, right? So we will get, if you do it, we will get something like this 108 degrees. So it is moving in this direction at this angle. Similarly, it will be just the mirror image, right? So it is in this direction and it will move like this. So this is to be precise because how will I know? Say this point is there. It can go like this. 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 So how do I know in what direction it is going? So for that, we have to calculate the angle of departure as well as angle of arrival if needed. So that's why this calculation we have done to check how it is moving. So is this clear how we have solved, or should I just repeat once again? So someone has texted. Okay, sir. Okay, so if the concept is clear, then we'll do the same thing. Let us plot using MATLAB. So the numerator is 1 and 2. So 1 and 2 s plus 1. And the denominator now has two inputs. So I don't need nested CONV uh, function. I will just use single CONV. And then the first polynomial is 1 and 3, right? S plus 3. Now the second polynomial has s square plus 2s plus 2. So let me run it and then check. So in the numerator, I have s plus 2. Denominator, I have, sorry, numerator is s plus 2. Denominator is s plus 3. See, I have made a mistake. So here I can see that I have made a mistake, else we will not be able to identify. So that's why I was displaying. So numerator is s plus 2, denominator is s plus 3, s square plus 2s plus 2. Let us see how the figure is looking like. So this is going in this direction and these two are going in this angle. So we know that now the angle is around 108 degrees. So if you see, it will also be close to 108 degrees. So this is just 90 plus some angle. So at this angle, it is leaving. So is this clear how we have drawn the root locus for this case? Yeah, Chidananda says yes. Amaresh, is that clear? Just to check whether our calculations are correct, s square plus 2s plus 2. Now we'll get pose -1 plus or minus j. So I'll give both the codes so that you can play with those and then you can understand how to use them. So if this is clear, then I'll move to the final two rules of today's discussion, which are 8 and 9. Yes, okay. So 8 and 9, they are also kind of together. Let me start with rule number 8, then I'll go to rule number 9. So first rule number 8. Rule number 8. So if you see in certain cases, the root locus is not touching the imaginary axis. In certain cases, it is going to touch the imaginary axis, right? At some point of time, it will cross. So the rule number 8 is about hitting the imaginary axis. So the intersection point of intersection point of root locus can be obtained using Routh-Hurwitz criterion. So whatever we have studied last week, Routh-Hurwitz criterion. So using this criterion, we will be able to calculate that intersection point and also the gain. And how to calculate the gain? Again, at that intersecting point. So that we can do from the this equation, this one. So this is basically rule number 9, which we have already discussed at the beginning. So we have added two more points. One is when it is intersecting that point, which is the imaginary axis, the intersection point of root locus and imaginary axis. So my bad, let me just write root locus and imaginary axis. So why this is important? Because once it crosses imaginary axis, it is entering the RHP, which means it is unstable. So we are checking the boundary for stability. So this is the point. So okay, I'm just changing the color. So basically 8 and 9 points are to find out whether if it is crossing the imaginary axis, we'll obtain that using Routh-Hurwitz criterion. And also once you get that point, you can calculate the gain from here. or you can calculate from the Raoult-Hurwitz criterion only. So anything is fine. So this is rule number 8 and 9. Again, we'll apply to one of the problems that I have considered so that it will make our life simpler. So k by s plus 2, s plus 4, s plus 6 is one problem that we have considered over here. So I will just copy paste this. And basically now what we are asking is k into s plus 2, s plus 4, s plus 6, which we have solved. Draw the root locus and find the gain at which root locus intersects the imaginary axis. So I'll just minimize this and then I'll put it here. So now basically what we are asking is, we know that this is going to hit at some point, right? And this is also going to hit at some point, and both are symmetric, of course. So we are asking what is this point? Similarly, what is this point? So this we can obtain from the Raoult-Hurwitz criterion. So 1 plus g of s is equals to 0, right? So from the Raoult-Hurwitz criterion. So we'll apply Raoult-Hurwitz criterion. So 1 plus g of s is equals to 0. So now we have to apply it for this. So now we'll get s plus 2 into s plus 4 into s plus 6 plus k is equals to 0. And if I'm not wrong, we have already expanded this. So it is s cube plus 12s square plus 44s plus 48. S cube plus 12s square, s cube plus 12s square plus 44s plus 48. So now I'll get k plus 48 equals to 0. Is this clear? Everyone?
Yes, sir.
Okay. So now I'll apply Raoult-Hurwitz criterion. So we'll start again. This is s cube. So we'll start from s cube, then s square, s to the power 1, then s to the power 0. So if you have gone through the last week, you'll know we'll start from s cube, then it will be s to the power 4. Then this will be 12, and then again here we have k plus 48. K plus 48. So if we calculate s to the power 1, then we will get product of 12 into 44 minus k into 48 by 12. So if we calculate that, we will get 12 into 44 minus k plus 48 by 12,
12.
right? So again, this is the first term. Maybe I'll write it smaller. Second term is 0 because we don't have anything on the second term is 0. So this term will be 12 into 44 minus of k plus 48 by 12. So in order to be on the marginally stable or on the imaginary axis, we know that this guy value should be 0, right? So if you do that, then you can calculate k is nothing but 12 into 44 minus 48. So to calculate that again, I'll use my MATLAB as calculator. 12 into 44 minus 48. So it is 480. So for k equal to 480, for k equals to 480, so I got k is equals to 480. For k equal to 480, that value is becoming 0. So now if I replace this one, everything, I am getting this as 0 and this also is 0. So entire row is becoming 0, which means the polynomial above that is called auxiliary polynomial, right? So this is my auxiliary polynomial, which is 12s square plus k plus 48 is how much? 528, right? 528 equals to 0. So now I have to differentiate it to get the
24
24 and then 0.
is equal to 0.
And then this will become 528. So now if I solve this auxiliary polynomial, they are the roots of the closed loop, right? So I will get s square is equals to minus of 528 by 12. So now if I calculate this, I'll get how much? Square root of 528 by 12, right? So square root of 528 by 12. So it is 6.36. So my s is equals to plus or minus j 6.36, or how much was that? 6.63. So at gain 480, if I calculate, my pole is on the imaginary axis and its value is 6.63. So either using this gain equation we will do, or we can do using Routh-Hurwitz. So Routh-Hurwitz is much more comfortable. So we can solve from there. So what we have done here, whenever this is crossing the imaginary axis, in order to find that point, we'll use Routh-Hurwitz criterion and then make the first element 0, because that is the marginally stable case, because we have poles on the imaginary axis. Once we have made 0, we can calculate the poles, and this will also give the frequency of the oscillations if they ask. So this is the last rule, 8th and 9th rule of the root locus. So now I can verify this whether it is correct or wrong. So again, we'll go back k by s plus 2, s plus 4, s plus 6. So let us go to MATLAB. Now k by means numerator is 1. Here s plus 2, s plus 4. Then I have nested CYNV function, CYNV. Then I'll add s plus 6. So comma, so this comma s plus 6, and then I'll check first whether the transfer function is correct. 1 by s plus 2, s plus 4, s plus 6, it is correct. So now this is what we have already previously checked, but now we are interested about this intersection point. Again, it is symmetric. So one point if you check, we are basically checking the other point. So now if I zoom in this point, it is close to 6.63, right? Now if I click on this point, it will give me the gain information. See, gain is exactly 480. So gain 480, basically gain is moving from how much? Gain is moving from, if I delete this, so from k equals to 0 to k equal to infinite, it is moving in this direction. And at k equals to 480, it is crossing the imaginary axis, which means if I maintain my gain less than 480, system is stable. Is that clear? Is this concept clear until this point? Both of you, Chidananda and Amresh. Using this rule, we are finding the marginally stable case, or the gain at which the system is marginally stable. And also we can find the poles using Routh-Hurwitz criterion. Clear, or any queries?
Clear, sir. All clear, sir.
Okay, okay. So now let us solve one problem. Now we basically combining all the rules, and then we are solving this problem. Okay, so both said yes. I think then we'll again start from rule number 1, and then we'll do slowly. So what is rule number 1? Number of poles and number of zeros. So how many poles are there? How many zeros are there? And what are the poles? What are the zeros also? You can add. How many poles? How many zeros? Okay. Chidananda says 2 and 2. So number of poles are 2. Number of zeros are 2. So poles are -1 and -2. Zeros are 3 and 5. So zeros are on the RHP side. Okay. That is okay. That is fine. Now the second rule. Second rule says NP minus NZ will. So again, from here I can say the branches are 2 because number of poles are 2. So branches are 2. And the branches that are tending to infinite are NP minus NZ, which are 0, because there are 2 poles and 2 zeros. So poles will start, the root locus will start at the pole and root locus will end at the 0. So now we have to see how it will start, how it will end. So now we are moving to point number 3. So point number 3 says root locus on the real axis, where it is exactly. Okay. So if the branches are not tending to infinite, say if the branches are not going to infinite, then there is no question of asymptote or there is no question of centroid. So that should be very clear. So there is no question of asymptotes because they are not going to infinite, right? No question of asymptotes or centroid, which means 4, 5 are not necessary. So we are basically not calculating asymptotes or centroid because poles are not going towards infinite. Poles are going towards 0. So 4 and 5 rules are not needed. So which we can directly skip and go to point number 6, which is breakaway point or break-in point. So that we will see. But let us quickly draw the axis and then let us see what is needed and what is not. So if you have any queries, please stop me at this point, else I'll just proceed. So I will consider the real axis at the center, I mean this imaginary axis, because I have -1, -2, 3 and 5. So I have -1 and then -2 here. It is 3. I will extend this. Three and 5. So again, this should be O because it is 0. Okay. So 3 and 5. So this is 3, this is 5, this is -1, this is -2. So now on the real axis, you tell me now whether on the right side of +5 root locus exists or not. So at least this problem you should be able to tell. Chidananda says no, sir. Very good. Between 3 and 5. So between 3 and 5. He says yes. Very good. So between 3 and 5, we have root locus. I think black is not visible. I'll shift to some other color. Maybe I can use green. And so here root locus is existing. So between -1 and 3. Between -1, 3 it exists? No. And very good. Between -1 and -2. Yes, very good. Very good. So between -1 and -2, it exists, meaning they are actually hitting. So they are hitting and then they are moving away. And similarly, between 3 and 5, their root locus exists because the after hitting, they will move away and then finally they'll reach zeros, right? So now before we make any comments, let us go to sixth rule, which says that dk by ds is equals to 0. So let us solve this and then we'll find out what is exactly happening. So someone mentioned why hitting. Yeah. So you are asking why they are hitting. So if the root locus exists between two poles, it means both the poles are moving towards each other. I'll show you one example. Um, if you consider this one, see if pole is moving towards 0, there is no hitting. Pole is moving towards 0, there is no hitting. Pole is moving towards 0, there is no hitting. Whereas in this case, two poles are moving towards each other, which means they will hit at some point because they are moving towards each other. So when they are hitting, then breakaway point will exist. If they are not hitting, breakaway point will not exist. So only when they are hitting, there is a question of breakaway point. So in this problem, pole is moving towards 0, so there is no hitting point, and they are moving towards infinite, so there is no hitting point. So breakaway point is not there. Whereas in this problem, two poles are moving towards each other, which means there will be a hitting point, and I have to solve dk by ds to solve for the breakaway point. So Chidananda is saying when it is moving to 0. So when it is moving to 0, that will be understood by checking on the real axis where the root locus exists. So if my rule number 3 says that the root locus exists between a pole and 0, pole will always go to 0. There is no hitting. But when my rule number 3 says there exists a root locus between two poles, then it means then it is hitting because both are moving towards each other, right? If the root locus exists between two poles, they are moving towards each other. If it exists between pole and 0, it means the pole is moving towards 0. But now here it says it exists between poles, it exists between 0. So this is somewhat different example. So that's why I have taken. Now let us solve for dk by ds equals to 0 and then let us see what we will be getting. So dk by ds equals to 0 means I will have to calculate from 1 plus k into g of s equals to 0. So from this I'll get k equals to -1 by gs, which means minus of s plus 1 into s plus 2 by s minus 3 into s minus 5. Is this clear? And then I have to calculate dk by ds is equals to 0 to solve for s. Is this clear, Chidananda? Yes, sir. Okay. So just to save time, I am not solving this. I'll directly give what are the S that you will get. You can solve during your leisure time because I would like to solve one more problem. So this is just a math that I'm pretty sure you will be able to solve. So this is 3.81 and minus 1.45. So let us see what is 3.81 and what is minus 1.45 location. So 3.81 is somewhere here. Minus 1.45 is somewhere here, which means based on the location of the root locus as well as the location of these points, I can say one is breakaway, one is break-in. So which is breakaway? The point where poles are hitting, it is called breakaway. So this will be, so that's why it is an interesting problem. This is breakaway. This is breakaway point. And this is break-in point. Okay. So now, because they are hitting here and then they will meet here again. So how they are moving? So they will hit here and then they will move to this break-in point. Okay. And similarly, it is going in the opposite direction. So now this is going in this direction. This is going in this direction. Once they hit, one will go to 3, one will go to 5. So this is the way the root locus looks for this problem. Is this fine? Yes, sir. So let us check whether the drawing root locus is correct or not using MATLAB. So k into s minus 3, s5, s plus 1, s plus 2. So I will use this function only one CONV, not two. So in the numerator, I have 1, minus 3, 1, minus 5. In the denominator, I have 1 and 1, 1 and 2. Let me just check. 1 and 1, 1 and 2. Yeah. So now let us first check the transfer function is s minus 3, s minus 5, s plus 1, s plus 2. Now let us see. So it is also correct. These two are hitting and again they are meeting in between and one is going to 0, other is also going to 0. So in this way, we will draw the root locus. But there is also another part of the question that I have asked, which is find the root locus at which it intersects the imaginary axis, which means we have to do the Routh-Hurwitz criterion. So for a Routh-Hurwitz criterion, we have to consider 1 plus g of s. So let us quickly do Routh-Hurwitz criterion. So we have 1 plus g of s is equals to 0, which means we have 1 plus k into s minus 3, s minus 5 by s plus 1, s plus 2. So Chidananda, I hope you are following. So if you do this s plus 2, then we'll have s square plus 3s plus 2 plus ks square minus 8ks plus 15 is equals to 0. So if you calculate this, we'll get 1 plus k into s square plus 3 minus 8k into s plus 15 plus 2 equals to 0. So from here, 15 plus 15k, sorry. 15k plus 2 is equals to 0 and 15k plus 2 equals to 0. So in this case, we need not even draw the Routh-Hurwitz because I can say that if this is equals to 0, then the poles are on the imaginary axis. So I can directly say right away, k is nothing but 3 by 8. Is that clear, Chidananda? Because if k is equal, this is 0, then s square is imaginary axis. Yes. Okay. So now if you calculate for s by substituting k equals to 3 by 8, you will get, I'm also not doing the calculations, I'm just skipping it because it is just basic math. So you'll get plus or minus j 2.35. So now let us see whether the gain is correct or wrong. And S is 2.35. So how did I say K is 3 by 8? Because S term I can make 0 and S square will be, basically S will be imaginary. So K is equal to 3 by 8. So what is 3 by 8? Let me calculate. It is 0.375. So let me check whether the gain is here same or not. So first of all, the point is 2.35, which is what I have mentioned. So let us check the gain. So this gain is how much? 0.375. So gain is also matching, which means our calculations are correct. So in this way, we can calculate at what point it is hitting the imaginary axis. So as long as the gain is lesser than that, our system is stable. So is this question clear, Chidananda? This is also a different question where we have zeros on the RHP side and then we are solving. Okay, and he says yes, sir. Now I'll quickly solve one problem. This is also like simple problem, root locus. So this is the last problem for today. Yeah, please be patient and then solve with me. So we'll start with first one. So tell me what are the how many number of poles are here, how many number of zeros are there, and also how many poles. I mean how many branches will be tending to infinite. So he says 3 and 1. Very good. So there are 3 poles, 1, 0, and NP minus NZ is 2, which means some of them are going towards infinite. So now we have to calculate asymptotes as well as the centroid point. So before that, for the point number 3, let us see the root locus on the real axis. Okay, this will check. So root locus on the real axis. So let us quickly draw the uh, this. So we have 0, -1, and -10. 0, -1, and -10. So -10, -1, 0. And pole is at -1.5. So pole is at -1.5. So with respect to rule number 3, can you tell me whether between which regions, you only tell me directly between which regions root locus exists on the real axis? So you tell me range 1 is this, range 2 is this, range 3 is this, wherever it exists. So now I will ask you questions, you answer so that I know whether your concept is clear or not. Yeah. So checking, you said -1 and 0. Yes, very good. -1 and 0. Any other region? -10 and 1.5. Very good. Okay. So now this is the way it is, right? So now let us see -1 and 0, whether they will hit or not. Chidananda? Yes, you said it will hit. So we have to find the breakaway and break-in point. Okay, we'll do that. So because there are asymptotes, so one of these pole will move to the 0 and 2 poles will go towards infinite. So let us find the angle of asymptotes as well as the sigma A. So angle of asymptotes is phi A equal to plus or minus 2k plus 1 into 180 degrees by number of poles minus number of zeros. So it is plus or minus 2k plus 1 into 90 degrees. So we'll get 90 degrees and 270 degrees.
270.
Yeah, very good. So can you calculate sigma A also, which is summation of poles minus summation of zeros by number of poles minus number of zeros.
1.5, sir.
Sorry, how much?
1.5, sir.
1.5. Number of poles. Poles are 0, -1, -10. Zeros is -1.5. Summation of poles minus summation of zeros.
So 0.5, sir.
How you are saying 0.5? What is summation of
So
poles?
0, sorry, sir. 10 plus 1, 11, 11 minus 1.5. 1 minute, sir.
Okay.
2.375, sir. Sigma
Okay,
is equal to 2.375.
okay, I think you are making mistake, both of you. I'll just solve. It's almost 8, so I'll just quickly solve. Sigma p is -1 minus 10. Sigma d is yeah. So it is minus 1.5 by number of poles minus number of zeros is 2. So we'll have minus 11 plus 1.5. So it is minus 9.5 by 2, which is minus 4.75, right? Agree? Both of you? Yes, okay. So these are the asymptotes. So we know if these are the asymptotes, two of these poles are moving along this way, okay? And these are going to hit and then they are going to move away. So let us see how it actually looks like. So now 4 and 5 are done. Now 6 is breakaway point, right? So 6 if you calculate, because we know that they are going to hit. So now I have to calculate the breakaway point. So dk by ds is equals to 0. If I do this, then what is going to happen? So let us see. So dk by ds, if you calculate, I'm just telling you, I'm just skipping the math. So we'll get s is equals to minus 4.36 minus 2.76 and then minus 0.6. So let us see where these points actually are. Okay, then we can make something out of it. So dk by ds is, you have to calculate k in terms of s and then differentiate it to get these points. So s is minus 4.36. So first this point is minus 4.75. So this point is minus 4.75. So we have one point at minus 4.36. So it is somewhere here. Okay. And then other one is minus 2.76. So it is here. And then one is minus 0.6. So it is somewhere here. Is that clear? Everyone? Yeah. So what I do is I just shift it like this. Okay. Just to have more space. Yeah. So now if you see, this is a little bit tricky. Minus 1.5. So we know that the pole will move towards 0. So it will move towards 0. And then now these two guys, what happened? These two guys are there, right? So they are hitting at this point, right? This is moving like this is moving like this. So one is breakaway point, one is break-in point. So this is breakaway point, this is break-in point. So these two guys, after hitting here, they will meet at this point, okay? So they will meet here, this guy, and then they will meet here. These two guys will meet here. And once they hit, again they will move away, right? So one pole is moving towards 0 and the other pole is moving towards the other pole. So now this pole which is moving initially with 0 and this pole which has now come here, they both will hit at this point. So this is the crucial point. They both will hit at this point, and now these two will go along the asymptotes. Is that clear? It is a little bit tricky because I got dk by ds 3 points, which means there are more than one breakaway break-in point. So first these two poles will hit here and then they'll come here and one pole will move towards the 0 and the other pole will hit with this pole and then now they'll move along with the asymptotes because asymptotes are also there, right? Two poles are supposed to move along the asymptotes and then there are three breakaway points. I mean, three solutions. One of them may be breakaway, one of them may be break-in. We do not know. So now fitting all the solutions of this dk by ds equals to 0, and they are also supposed to move along the asymptotes. In that way, whatever is fitting, this is how we'll get the understanding of the root locus. So this is a little bit tricky problem, so that's why I have considered and I wanted to solve in today's class. This may be a little bit tricky, but the overall guidelines, if you follow from 1 to 8 and 9th point, then it will be clear. In this problem, there is no question of 7 and 8 and 9, because they are not crossing the imaginary axis. And 7 is also not, we are not calculating angle of departure because we got some understanding. Is this clear, this problem? Or should I just re-explain what has happened? Sir, here three cases. Yes, Chidananda. So here there are three cases because all the three are part of the root locus, right? So if they are not part of the root locus, they don't mean anything. But if they are part of the root locus, they mean something. So first, that's why I have plotted those points. And then I have seen what could be the direction of or the movement of the poles, so that they will move along the asymptotes also and they will meet at this point. So there are almost three collisions that are happening in this problem, which is a little bit tricky. But based on the movement, we can understand. Say these will break away at this point, and at this point or at this point they have to break in. They cannot break in at this point because then it will cross multiple times, so they have to break in here and again break away here. So that's how we got it. Sir, can you explain again hitting and moving to 0? Yes. So basically, I will, I think, redraw it -10, -1.5, -1, -0. So I'll just quickly redraw. So we have -10 and then -1.5 and then -1 and then 0. So the breakaway point, one is here, another one is here, and then the asymptotes were here, something like this. So now what I initially figured out is I have figured out that root locus exists in this path as well as in this path, which means all the three solutions of the dk by ds has some, like some reason why it is there. So all of them has some significance. But first, these two poles are moving towards each other and then they will hit here. Okay. So now once they hit, they will move away and then they'll move towards the pole. So in these 2 points, they can meet, but they can't meet at this point because then, say, let us assume that they are meeting at this point. Okay. Both of them are coming here and then meeting at this point means one is going here, one is going here. And now this pole that is coming here will also hit, right? But there is no breakaway point. So this is not the way they are meeting. So they are meeting at this point, the first point. So this is coming here, this is coming over here. And then they are hitting here, and one is going in this way, one is going in this way. So now the pole that was coming in this way will hit with this pole, and they both will hit here. Now, how are they moving? They are moving towards the infinite along the asymptotes. So this is one asymptote, this is the other asymptote. So this is a little bit tricky compared to what we have considered previously in today's discussion. This is not so straightforward because there are 3 points. So is that clear? Yes. Okay. Let us also plot it in the MATLAB. 1 plus s.5. So we have numerator 1 and 1.5, and the denominator we have s. I'll combine two. So s square plus s. One is s square plus s plus 0. Other is s plus 10. So let us first check whether the transfer function is correct or wrong. 1.5. So it is not 1.5. It is s plus 1.5. So I made a mistake. Sorry. S plus 1.5, s into s plus 1 into s plus 10. So let us check. Yeah. So basically what is happening? So these two are, if you see the blue will mark the direction of one pole. So this pole is hitting with this pole, coming over here, and it is going to 0. The other pole is hitting with this one, coming over here, and then again hitting with this, and then going towards infinite. This pole is hitting with that pole and coming towards infinite. So there is 1, 2, 3. Total 3 hittings are there. That's why it is a little bit tricky. But if you follow the guidelines and then go by rule, then it will be easy. Okay, I think we have already crossed 8 o'clock today. If you have any doubts, I'll explain, else I'll quickly summarize and then we'll end this session here. And this is week 5, right? If I'm not wrong. Check. Okay, nice explanation, sir. Thank you. Yeah, thank you, Chidananda. So I'll just quickly summarize. So this week is all about root locus, which is a graphical method to study the closed loop poles movement as the system parameter k varies. So beginning we had some discussion regarding characteristic polynomial and what are the closed loop poles. But for plotting the root locus, we will have 9 rules. We have to follow one by one. So first root is about number of branches, which are equal to number of poles, and second root is about number of branches that are terminating at infinite, which is np minus nz. And third is any point on the real axis lies on the root locus if number of poles and number of zeros on the right hand side of that point are odd number, which is very critical. And then we have solved one problem which will fit in those 3 rules only. Then we have learned about 4 and 5, where this will happen only if there are branches that are terminating towards infinite. If they are not terminating, then there is no point of these 2 rules. So in such case, we have to find the angle of the asymptotes and the intersection of the asymptotes, which is called the centroid point. So using this, again, we have solved one problem, which will again fit in this problem. And we have found the asymptotes and angle of asymptotes. Sixth rule is about breakaway point, and we have to solve by dk by ds equals to 0. And we have to see the solution of this, whether that is part of the root locus or not. If it is not part, then we can discard it. If it is a part, then it will have some significance to it. And then we have solved another problem, and we have seen where they are hitting and how they are moving. And then we have discussed about rule number 7, which is angle of departure or angle of arrival. So in this case, this is the equation using which we have solved one problem, and we have understood how is the angle of departure slash angle of arrival. And rule number 8 and 9 is about intersection with the imaginary axis, and it can be obtained by using the Routh-Hurwitz criterion and considering the first element to be 0. So here also we have solved one problem and saw that at what gain it is hitting, and then we have also done it in the MATLAB, and we have solved 2 more problems just to understand overall picture of the root locus. So here I have considered one problem, and the last problem is a little bit tricky because here dk by ds has 3 solutions and all 3 are part of the root locus region. So that means there are 3 hitting points. So that is what you should keep in mind, and then you can make a story from that, because you can consider one assumption and that will not make sense. Then you have to consider other assumption, and then you have to fit the root locus such that it will follow all the 9 rules. If there are 9 rules, here there are 6 rules, so part of 6 rules. So that's all about week 5, which is this root locus. So I'll meet you again on next Monday with week 6 content. I wish you all the best for your assignment 5 as well as assignment 4, I guess. So yeah, please solve and please go through this video if you have any doubts. I'll try to upload by tomorrow. Is that clear? Okay, if you don't have any doubts, then we can end this session here. See you again on next Monday. Thanks for joining and making it interactive. Okay, I'll end this session here then. See you. Good night.